been the world's deadliest force of nature.
A hypercane is a really, really, really intense hurricane. They can be up to 20 miles high, and that actually punctures right into the stratosphere and the ozone layer.
These storms are huge. A hypercane has winds theorized to be 500 miles per hour.
But could a hypercane have caused the most famous extinction in Earth's history?
To have total extinction of the dinosaurs, you've got to have a mechanism that would kill things around the entire planet.
Was there a prehistoric megastorm so explosive it wiped out 75% of life on Earth? And could it happen again? 65 million years ago, an asteroid hurtles through space on a deadly collision course.
The rock was a piece of an asteroid that was maybe the size of Manhattan Island.
Speeding at 30,000 miles per hour, the asteroid faces no resistance until planet Earth gets in the way. A blazing trail of smoke and fire follows the 6-mile-wide asteroid as it cuts through the atmosphere. Its final destination is a tranquil patch of ocean near Mexico's Yucatan Peninsula. The force of impact is beyond anything we could imagine.
The amount of energy involved here is colossal. It's 100 million megatons, where 1 megaton is an average-size hydrogen bomb. 100 million hydrogen bombs going off all at once on the coast of Mexico.
A lot of life within a reasonable distance, the impact would be wiped out just by the heat, the blast wave, tsunamis.
The impact zone instantly becomes a red-hot cauldron. Seawater begins to rush back into the 20-mile deep crater, sizzling and smoking like water on a hot frying pan. As the fiery hole fills in, steam gathers over the ocean. Heat pushes the water vapor skywards, which begins to condense and form storm clouds that rise high into the stratosphere. The surface temperature of the ocean has risen to an incredible 120 degrees Fahrenheit. This extreme temperature is the key to a megastorm, which may have been the greatest force of nature in the history of the world. A hypercane.
A hypercane is a very strong hurricane that goes well up into the stratosphere. Today's hurricanes only go into the lower stratosphere at best. These go almost twice as high physically into the atmosphere. It's almost between a tornado and a hurricane in size, and potentially very destructive.
Only 10 miles across, a hypercane is smaller than an average hurricane. But at 20 miles up, the megastorm is double the height, reaching into the stratosphere.
These would be very noisy storms. They would be generating a continuous roar, like a jet engine, on top of everything else going on that you normally have in a windstorm, and thunder and lightning.
The ultimate force behind a hypercane is its wind, which can reach incredible speeds of over 500 miles per hour, more than 2 times faster than the most powerful hurricanes.
If you have a wind speed that's twice as strong in one hurricane as in another hurricane, it doesn't mean that hurricane is twice as powerful in terms of its wind force. It means it's actually 8 times more powerful, because it's the cube of the wind speed that determines the impact on people. So if you take 180 mile an hour winds, if you go to a 360 mile an hour wind, that wind will be 8 times more powerful still. And in hypercanes, we're talking about even potentially more powerful winds. So that gives you a sense of just how incredibly powerful hypercanes are theorized to be.
You're getting close to the speeds of sound when you get up to those 500 mile an hour speeds. You know, drive down the highway at 70 miles an hour and put your hand out, and you'll appreciate the kind of force that can accrue on a building structure under those kinds of circumstances.
But did this prehistoric megastorm really happen? If it did, the hypercane would be more than just a superstorm. It may also be the latest suspect in the greatest murder mystery in our planet's history. The extinction of the dinosaurs. Around the world, the fossil record bears witness to a single defining moment in the Earth's evolution, a worldwide catastrophe. When 75% of all life was wiped out. An event that gave rise to the age of mammals, paving the way for humans to rise to the top of the food chain. An event known as the KT extinction, which Kirk Johnson has been studying for years.
In the KT boundary, the K is an abbreviation for Cretaceous, and the T is an abbreviation for Tertiary. So the KT boundary marks that point in time when the Cretaceous period ended and the Tertiary period began. We're on the banks of West Bijou Creek in the plains of eastern Colorado, and it's just a grassy gully, but what's exposed here are layers of mudstone and sandstone that were deposited at the bottom of the lakes and ponds something like 65.5 million years ago. So from my toes to my shoulder is 20,000 years of Earth history. Right in the middle of that is the KT boundary, and it's an amazing thing because below this level we find the rich world of the Cretaceous, dinosaurs, whole diversity of plants, ammonites, flying reptiles. Above the layer, there's none of those things. It's a different world. This is the age of the mammals above, the age of the reptiles below. And it all happened at this point in time, a single instant 65.51 million years ago.
For decades, scientists only speculated about what could have been responsible for such a massive extinction. Could a global plague have killed the dinosaurs? Did extreme climate change wipe them out? Then in 1980, physicist Luis Alvarez and his geologist son, Walter, turned up a startling new piece of evidence. While examining the rock layers of the KT boundary, they discovered a layer of clay that had high levels of iridium, a chemical element that shouldn't be there.
Iridium is a platinum group metal that's rare on Earth's surface, and it's more common in asteroids, meteorites. So when Walter and Luis Alvarez found anomalously high amounts of iridium, they realized it might just be a large amount coming in all at once in the form of an asteroid or comet. And that was really the seed of the whole idea of an asteroid causing extinction.
All around the world, samples of this KT boundary clay showed a huge spike in iridium levels occurring at the same time. The evidence to support the Alvarez impact theory was becoming clear.
There was anomalous iridium at KT boundary sites all around the world. I've found several myself. And when you go to outcrops like this, you can put your finger on the debris, and below that layer are dinosaurs, and above it there are none. It was one of the great discoveries in Earth history.
The Alvarez team calculated an asteroid 6 miles wide crashed into the Earth and spread the iridium around the world. But there was still one mystery to solve.
In 1980, when the asteroid hypothesis was first proposed, one of the first questions was, okay, where is the crater? The Alvarez's proposed an asteroid impact crater that would be about 100 kilometers in diameter, so it was a really big one.
There was no known crater that size anywhere on Earth. But in a twist of fate, around the same time the Alvarez team proposed the asteroid theory, oil companies found evidence of a massive crater on the sea floor next to Mexico's Yucatan Peninsula.
If you went to Mexico today to look for the impact crater, you would not see much. But interestingly enough, these wells called cenotes, these Mayan holy wells, where you can go snorkeling and scuba diving today, these clear, deep wells in the limestone, if you plot those on a map, they make this very interesting semicircular pattern.
By the 1990s, with the evidence from the KT boundary and Yucatan crater, the majority of the scientific community accepted that an asteroid triggered a worldwide apocalypse 65 million years ago. But questions still remained. the asteroid only impacted one small part of the planet. What ultimately killed 75% of life around the world?
Problem with that is, to have total extinction of the dinosaurs, you've got to have a mechanism that would kill things around the entire planet.
There's lots of room for speculation. There's lots of ways to take the things that you know must have happened based on physics when you have an asteroid strike the Earth, and then play those out as scenarios and say, well, you're going to get tidal waves that are really huge. You're going to get earthquakes that are massive. You're going to get acid rain. You're going to get regenerating ejecta. All those different kinds of things will kill in their own particular way.
One prominent theory involves massive firestorms which transform the entire Earth into a broiling oven. Almost immediately, anything above ground was incinerated.
So the picture we've got is the asteroid hits Mexico. The whole sky around the planet turns red hot. If you spread that evenly around the planet, it's the energy of a 1 megaton hydrogen bomb every 6 kilometers. Fires are ignited everywhere below where there's any fuel and burn with blast furnace intensity for a couple of hours. The entire biomass that was involved in this was reduced to ash. Not even charred tree stumps, not even charred dinosaur steaks.
Another theory suggests the asteroid impact propelled massive amounts of debris into the atmosphere, causing the Earth to heat up.
The estimates are about 6 to 7 times the present day levels of carbon dioxide. The analogy has been like putting a blanket in the atmosphere to trap thermal radiation so that the planet actually warms.
But in 1995, MIT professor Carrie Emanuel proposed a fascinating theory. Did the asteroid impact trigger a series of megastorms, which led to the death of the dinosaurs? "65 million years ago, life on Earth changed forever when a 6-mile-wide asteroid crashed into Mexico's Yucatan Peninsula. In the wake of the impact, 75% of all species on Earth vanished. Could a single asteroid be the lone killer? Theories about what happened after the impact have come from all corners of the scientific community. Ideas ranging from global warming to worldwide firestorms have been put forth. But no single idea has proven to be the smoking gun.
One thing you might ask is, well, okay, the asteroid hit. What did kill the dinosaurs? I mean, the asteroid struck. The ones that were right below it obviously were killed by the asteroid directly. But what were the subsequent killing mechanisms that knocked off dinosaurs worldwide? Was it the fires that were lit by the regenerating ejecta? Was it the fact that it was dark for a year and the food wasn't growing in the form of plants? Was it the fact that there was acid rain? Lots of different things that might explain why dinosaurs didn't survive the KT boundary impact or its immediate effects.
In 1995, a new theory added a twist to the debate. It suggests the cause of the most famous extinction known may have been the most powerful megastorm ever seen. But the man behind this theory, Carrie Emanuel, was not looking for what killed the dinosaurs. Instead, the MIT professor, an expert on hurricanes, accidentally discovered a hypothetical superstorm, the hypercane. In the 1980s, Carrie Emanuel and scientist Rich Rotuno were creating computer models to determine what causes the most violent hurricanes to form.
We try to get at the basic physics of hurricanes, trying to understand the nature through a hierarchy of models.
Hurricanes get their strength from warm oceans and begin to form when the surface temperatures reach about 80 degrees. Even warmer temperatures means a more intense storm.
We noticed that if you push the ocean temperature too high, that we couldn't find a solution to this set of equations. There are combinations of parameters for which the answer is infinity. Okay, that's what we call singularity. It really doesn't have an answer. They were trying to tell us that the usual physics that control the intensity of the hurricane break down at some point and run away into a completely different state. We eventually coined the term hypercane to describe what kinds of storms would form when you exceeded this limit. So I went to Rich Rocchino and said, do you think we could model one of these? Could we build a computer model that would handle these very special conditions? And he thought that was possible.
With a model, one's able to go in and actually control certain things which you can't control in nature. We were putting in things like 50 degrees Celsius, very, very hot sea surface temperature. So it didn't take much to get this hypercane going.
The model predicted potential wind speeds of over 500 miles per hour. Forces never known on planet Earth.
It dawned on us that this was real and that it was trying to tell us something about nature.
But to create a hypercane, the ocean would have to be heated to a temperature of 120 degrees Fahrenheit. There was a problem. That kind of surface water temperature does not occur anywhere on Earth. Even in the tropics, water temperatures rarely reach over 90 degrees. To form a hypercane, there would have to be a tremendous trigger or release of energy, one that could superheat an area of water beyond anything ever recorded.
How do you heat a patch of the ocean up to very high temperature? We imagined that some kind of external body like an asteroid had collided with the Earth and superheated a patch of ocean water maybe 100 miles across up to a temperature of about 50 degrees centigrade, which is very hot. It's well over 100 degrees Fahrenheit. Then almost immediately, within a day or so, you would probably develop a hypercane.
Could an asteroid have unleashed a hypercane 65 million years ago? For now, hypercanes still live in the world of computer models. But to understand the physics of how they work, you don't have to go too far in the real world. A hypercane functions much like a hurricane, one of the most powerful and destructive forces on Earth.
One way to get a handle on just how incredibly powerful even a standard hurricane is to ponder the fact that in just 20 minutes, the winds going into that hurricane and the heat released by the condensation and showers of thunderstorms in the hurricane, those together can release more energy than is produced by all the electrical plants across the planet.
In essence, hurricanes are heat engines. They convert heat energy into wind energy. The heat comes from the ocean and is transferred to the atmosphere as water evaporates.
The hurricane has to take that warm, moist air and get the energy from it. And it does that by cooling the air, turning it into clouds.
And those spiral into the center of the storm, pulling heat and moisture in with them. As the thunderstorms solidify around the center, you get a central core, and that acts like a chimney. The heat and the moisture pulled in by the thunderstorms actually travel up the sides of the eye wall and then disperse in the atmosphere, spiraling back the other direction as they exit.
That's what powers a hurricane. It's evaporation of seawater. That's why they die when they go on land.
As hurricanes move over warm waters, a feedback mechanism occurs within the storm. The spiraling air of the hurricane can't cool down because it's constantly in contact with the warm ocean. This same type of feedback runs wild in a hypercane.
It's that feedback that runs away in a hypercane. If you make the ocean too warm, that feedback becomes so powerful, the lower the pressure, the more heat flows into air that's trying to get into the center of the storm, which makes the storm stronger. It's a runaway feedback. And it runs away until the storm goes through a complete transformation into a hypercane.
You wouldn't be able to get the strong winds that are theorized for hypercanes if you simply expanded a regular hurricane and made it several times bigger. The key difference between a regular hurricane and a hypercane isn't so much that it's bigger, just that it's stronger and more intense.
Although hurricanes always make headlines, they are not as common as we might think. Many factors must come together for a hurricane to form.
You can think of it as becoming a Hollywood star. There's a lot of people out there with talent, but you have to have a lot of breaks and things happening along the way to get everything just lined up right for you to become a megastar.
One of which is warm water, at least 80 degrees Fahrenheit, is kind of a key parameter in today's climate for having hurricanes form. If it's only a very shallow warm layer, as the hurricane starts spinning up, it'll churn the ocean and mix it. So if there's cold water below, it'll self-regulate or not allow the hurricane to become much stronger. You also have to have an ingredient of very moist air. If the hurricane's over extremely warm water, but the air is very dry, the thunderstorms will sputter and the hurricane won't grow or intensify.
The final ingredient for a hurricane to form is a lack of wind shear. Any slight variations in wind speed through the height of the storm will kill the chances of a hurricane forming. Hurricanes. They are one of the most destructive forces on Earth. Each year, an average of 11 storms form in the Atlantic, although only about half of these hit land. But when they do, these storms pack winds that can reach over 150 miles per hour. This is Mother Nature at her most lethal.
We can see some very devastating results, either through the winds, the storm surge, the rain and the flash flooding, and tornadoes. Those are the threats that hurricanes cause when they come ashore.
Hurricanes pose one of the greatest threats to populations in both death and destruction. In 2005, the world witnessed one of the deadliest storms to ever strike, Hurricane Katrina.
Well, I think Hurricane Katrina pointed out to Americans and to the world just how vulnerable a city can be and how much damage a hurricane can inflict, even in this modern day and age. I think someone would have been astounded if you told them 10 years ago that a hurricane would strike the U.S. and kill almost 2,000 people.
The death toll left in Katrina's wake came from the massive floods, which drowned nearly 2,000 people when the storm surge overtook the city.
Almost every levee broke in New Orleans. 80% of the city was flooded. Windows were blown out. People drowned.
But the chaos and ruin left by Katrina would be nothing compared to the awesome force inside a hypercane. A powerful hurricane has the ability to kill and destroy a city. But could the greatest megastorm ever conceived be responsible for a worldwide extinction? In 1995, MIT professor Kerry Emanuel proposed that 65 million years ago, a prehistoric megastorm may have been the lethal force behind the extinction of the dinosaurs. Towering over 20 miles high, and with wind speeds of over 500 miles per hour, the hypercane would have been the ultimate display of nature's wrath.
There's no earthly analog to wind speeds like the kind that are postulated in hypercanes. The strongest wind speed ever measured on Earth's surface is 231 miles an hour.
Be like nothing you ever saw before. There would be a lot of lightning, so you'd see this sort of column of cloud that's very, very high, and maybe with a spread out mushroom shape at the top, illuminated by lightning, especially at night. It can be spectacular.
But the killer hiding inside this mighty storm wasn't the winds or lightning. Instead, the hypercane would have initiated a chain reaction that led to an invisible enemy being unleashed.
Most of the light from the sun is visible light, the kind you see and that warms us up, but there is a component that is invisible, that's in the ultraviolet range, and that can have profound effects on many, many forms of life and can be literally deadly.
Like a hurricane, the hypercane pulls water vapor through the eye wall and out of the top of the storm. But hurricanes only reach 8 to 10 miles high. Hypercanes reach over 20 miles into the stratosphere, home to the ozone layer, Earth's shield against the lethal ultraviolet rays of the sun.
In fact, that was what led us to ask, well, what would happen if you started to pump water into that part of the atmosphere? And we did some calculations to suggest that if you put a lot of water in that part of the stratosphere, it would destroy much of the ozone layer that protects life from ultraviolet radiation.
The theory is that the hypercane pulls water vapor into the stratosphere, where the sun's ultraviolet radiation breaks the water molecules apart. The water is transformed from H2O into OH and HO2, which steal oxygen atoms from O3, the ozone. It's a process which destroys the protective ozone layer that defends the Earth from the sun's radiation.
That radiation can kill animals, it can kill plants, it can kill marine life.
But what are the odds that one hypercane, a mere 10 miles wide, could inject enough salt water into the stratosphere to destroy the Earth's entire ozone layer? If there were only one hypercane, the odds are slim. But Professor Emanuel believes the red-hot crater left after the asteroid impact may have been heated for days, setting off a series of hypercanes that could inflict much more damage.
So we actually imagine that you would have a sequence of storms, and that sequence would last as long as the atmospheric conditions are broadly conducive and as long as that water stays hot.
If multiple hypercanes formed, the ozone layer may have been overwhelmed, suffering a complete breakdown that would unleash massive amounts of radiation on the surface of the Earth, quickly killing almost all life above ground.
Anything exposed to the sun would have real trouble under those conditions. I don't think it would take very long, probably a week or two, for this to happen.
But what of the 25% of species who survived? It turns out they had an advantage that the dinosaurs never did, paving the way for a new world order.
And it turns out dirt is a very good insulator. And so a burrow about a foot deep would have sheltered you from the heat. And if you ask the obvious question, what is it that likely had a population in burrows or in water at the time of the impact? It's mammals, turtles, lizards, frogs, snakes, alligators, fish. It's an exact match for what made it through.
So if you're bigger than a cat and you lived on land, forget about it. You're just simply not present in the rock layers above the KT boundary event.
However, the idea that a super hurricane could have ended all life on Earth has been met with skepticism by some.
I'm not sure what role the hypercanes played in the extinction of life at the Cretaceous. It's not clear that the destruction of ozone due to the storms was the cause of the demise of life on the planet.
There's nothing weak at all about the hypercane. I only argue that it didn't cause the extinction of dinosaurs because there weren't any dinosaurs left a week after the impact. But I do find the arguments for hypercanes and really strange weather after the impact very plausible.
What ultimately killed 75% of life on Earth after the asteroid impact? As of today, computers and the laws of physics show that hypercanes cannot be thrown out of the equation.
I don't think we took a negative view necessarily to any of the other ideas. It's not as though, gee, none of these ideas work, therefore we're going to come up with our own idea. It was more like we had an answer begging for a question.
A smoking gun has yet to be found. But is there any physical evidence left of hypercanes? What proof do we have of their existence? Could the answer be hiding in the geological record? It may have been the ultimate force of nature. The hypercane, a compact megastorm just a fraction the size of a hurricane, but theorized to pack a punch never seen before. Could hypercanes have been responsible for killing 75% of all life on Earth? The hypercane may be a theory, but is there evidence that this superstorm even existed? The place to look can be found all around the world. a 1-inch layer of sediment which has become the key to understanding what some scientists consider the world's largest crime scene. In the KT boundary lies the physical evidence of an asteroid strike over 65 million years ago. But does the KT boundary also hold clues to suggest hypercanes formed after the impact?
Well, that's a really excellent question, and we've given some thought to that. Can we find proxy evidence for hypercanes in the geological record?
It's possible to get some idea of where these hypercanes would have been impacting the coastal regions, and then to go and look if the geologic record is there to find some signature of those events.
One possible signature could be the fuel that fires the engine of a hypercane, salt water. Warm ocean water is the key to a hypercane's power. Could the salt from the ocean have left marks in the geological record?
The interesting thing, of course, is that you would ingest a lot of salt into a hypercane. Now, the salt that goes up into the stratosphere may not come back down as raindrops, and it might get spread globally and come back down.
But even if an elevated salt content could be found, important questions still linger.
The challenge, I think, would be how do you separate the deposits of a hypercane from the deposits of a tidal wave?
Even Professor Carrie Emanuel realizes the chances of finding definitive proof are slim.
The problem with salt is it tends to get dissolved and washed away. It might have happened. Whether it gets preserved in the geological record, I think, is somewhat dubious.
Science has yet to find the one telltale factor that could distinguish a hypercane in the geologic record. And although the evidence for hypercanes remains elusive, the question becomes, could hypercanes and other superstorms be part of our future? Warm ocean waters are the key ingredient to forming hypercanes and hurricanes, and many scientists see more severe hurricanes as a reality to come.
As the world warms up, the potential for stronger hurricanes increases. So one plausible scenario is you actually have fewer hurricanes. But the few that you did get, some of them would be very strong, stronger than hurricanes today.
But determining which hurricanes will become killers and which ones won't is still an elusive art. In fact, scientists don't know exactly what makes some storms form into hurricanes and others simply fade away.
We're very good now at tracking where hurricanes are going to go, but still challenged at determining how strong they're going to get. You know, what is that it factor?
We can't do hurricanes in a laboratory. We have to build computer models. Those of us even who do computer modeling aren't terribly confident about those models unless they can be compared rigorously with nature.
It may be impossible to recreate a fully formed hurricane in a lab, but at the University of Miami, Brian House is using new tools to observe the dynamics that occur between the ocean and the atmosphere during hurricanes. If ocean temperatures are getting warmer each year, this research could help determine which hurricanes in the future have the potential to explode in force. The tank can create winds of up to 134 miles per hour, leading to realistic hurricane conditions that can be tracked in a controlled atmosphere.
Those winds that we can generate here will interact with the water surface in the same way that the winds in a hurricane will interact with the water surface. We can look at detail at where the air and water meet and learn about how things move across that boundary.
The boundary between the wind and the waves is where heat transfer and friction take place, key components to determining a hurricane's strength. The lab experiments have led Brian House to a new conclusion about how intense hurricanes form.
It used to be thought that the friction increased in a certain way very quickly as the winds increased. And what we've been able to measure here is showing that that's true up to a certain point. And then the ocean surface becomes actually flattened by the strong winds.
A flattened ocean surface leads to less friction and an eye-opening outcome for Brian House.
That's been an important result because then it allows more intense hurricanes to develop than you might have thought previously.
These kinds of discoveries have been made possible by new optical technology. Lasers and remote sensors allow scientists to examine the properties of the water without physically touching it.
What you see behind me is a particle image velocimetry technique for using laser sheets and particles in the water, and this is a way that you can map the flow right up close to the air-sea interface. These are little 50-micron particles that we've placed in the water, millions of them, so that we can track where each little piece of the water is going. That can then tell you the slope of the surface at that same point. And from that height and those slopes, you can then determine the whole wave spectra, the whole characteristics of the ocean surface.
Scientists are now beginning a new era in hurricane research and getting one step closer to predicting how severe a storm may become. As deadly hurricanes and increased ocean temperatures become more common, scientists wonder, what will hurricanes of the future look like? Could there be a hypercane in our future? In 2005, Katrina proved one hurricane is all it takes to send a modern city into chaos and despair. Today, some scientists tell us Katrina is just the beginning. They argue global warming is raising the ocean temperature, and this will lead to more powerful hurricanes. Experts agree that areas near tropical waters face the greatest threat. Numerous cities in Florida and along the Gulf Coast of the U.S. would be caught in the crosshairs. But would any city be able to face the incredible force of a megastorm like a hypercane? The closest thing to compare to what we might see in a hypercane are Category 5 hurricanes, which can reach speeds of over 150 miles per hour. But only 3 hit U.S. shores during the 20th century.
Amazingly, in the United States, though we get many hurricanes, we've only had 3 Category 5s in the last century that have actually struck landfall as a Category 5. Those are the Labor Day hurricane of 1935 that struck the Florida Keys and killed a few hundred people there. Hurricane Camille, which struck the Gulf Coast in 1969.
The most recent was in 1992 when Miami and South Florida faced Hurricane Andrew, a storm that claimed 65 lives and caused almost $30 billion in damage.
In Hurricane Andrew, we had roofs blown away and even the walls blown down. Families hovering in a bathtub just for their own survival. There was almost total devastation in large communities.
And if that hurricane were to hit today, because of the population increases we've seen in the last 15 years, probably be looking at a double amount of damage.
A Category 5 storm like Andrew would be a light breeze compared to the power of a hypercane. But do we even think we could see a hypercane in modern times? It's a scenario hard to imagine. But Kerry Emanuel, the man who came up with the theory, notes that an asteroid impact like the one 65 million years ago isn't the only way to get the extreme ocean temperatures needed to kickstart the megastorm.
We thought extreme undersea volcanism might do the trick. Actually, if you go to the bottom of the Red Sea today, you find ocean water that's been heated by volcanism to temperatures close to the boiling point. There is some speculation, I don't know what to make of it, that once in a while the water becomes buoyant enough to come to the surface, and if that were to happen, then at least in principle you might get a hypercane out of that too.
If a hypercane ever came in contact with our world today, it would be one of the greatest disasters imaginable. Populations like Miami would have nowhere to hide. As the storm makes its way to landfall, the calm atmosphere gives way to an increase of wind and rain. Once the megastorm hits the city, the nearly supersonic winds uproot almost everything in sight.
You would definitely have to cancel your hair appointment. You would have total destruction. Very few, if any, survivors in that kind of an event. Very devastating event, something that's almost beyond what you are willing to contemplate.
Imagine what would be flying around in 500-mile-an-hour winds. We'd be dealing with moving glass, moving steel, moving concrete, moving wood, moving bodies, moving animals. Nothing would stay bolted down.
It stands to reason that a hypercane would leave very little, if anything, standing in its path.
Today, cities like Miami have strict building codes to protect against hurricanes. But those buildings would have little chance against a hypercane.
The factors that go into hurricane resistance design are many. Most of the country is designed for wind speeds of about 90 miles an hour, and as we get closer and closer to the coastline, it could increase to as high as 150. The hypercane is a wind force velocity that's well above our design standards.
Would it be possible to build a structure that could stand up to the winds of a hypercane?
Expect some sort of bunker-type building construction, perhaps, if you had to sustain those, perhaps earthen, covered in part to help not project above the Earth's surface, and so if you keep things relatively low and you make them relatively massive, protect the edges and that kind of thing against high accelerations by having rounded surfaces, you can build against even that kind of a disaster.
But even if something could be built to withstand the force of a hypercane's wind, the storm would still unleash a disaster for which mankind hasn't found the answer: the destruction of the ozone layer. They may never prove a hypercane destroyed the ozone and caused the death of the dinosaurs. But without the extinction of these prehistoric reptiles, evolution would have taken a very different road.
If the dinosaurs hadn't been eradicated, then I don't see any reason why they wouldn't be running around right now, and mammals would still be little rat-like things, probably. These mass extinctions are responsible for large chunks of what we're looking at today, and it'd be a different planet without them. Totally different.
So in some sense, you could say we're the end product of a series of these mass extinctions.
We may never know if an asteroid unleashed hypercanes, but experts agree the search can still yield useful answers for science.
I think hypercane falls into a class of really interesting and compelling ideas, and it's up to the next round of scientists to figure out how to test those. It's one thing to posit this thing. It may well have happened, but did it happen?
I think with theorized phenomena such as hypercanes, even if they never existed, it's a wonderful exercise to conceptualize them and figure out how they would operate, what role they could have played in history.
Frankly, I think there are some more straightforward explanations, potential explanations for mass extinctions. Even if it turns out to have no application to understanding the past, I'd like to see how they really work. So you learn a lot about nature, and ultimately you learn a lot more about the world you do live in.